We have an amazing keynote. Really privileged to have Valentina speak for us today, and she will be talking about the exploit development lifecycle from concept to compromise. Valentina Palmiotti, or as she's known on the internet as Chompy, specialises in low-level vulnerabilities, exploit development and offensive security. She is really an amazingly talented woman who has done Android, Linux, Windows, and a bunch of other things as well. So let's welcome her to the stage.
Thank you so much, Silvio, for that amazing introduction, and thank you, Kylie, as well, for inviting me to speak today, and all of you for being here. I was told that this is the biggest technical conference in Australia, so I hope to not disappoint. But my talk today is going to be on the exploit development lifecycle from concept to compromise. Oops. Oh no. Already. Okay, so thank you, Silvio, for introducing me. You may know me by my handle, Chompy. I'm a reverse engineer, a vulnerability researcher, an exploit developer, a post-exploitation developer, and I'm interested in all things offensive security. I've been in security for about 7 years. It's going to be 7 years this November. Time flies. I'm the head of vulnerability research and exploit development at IBM X-Force, where I oversee the use of using zero-day exploits and end-day exploits on red team engagements. I'm chronically online, professional poster, and as of this year, I'm a Pony Award winner. So a little bit of background on my motivations for this talk. I want to just talk about what I know best, which is exploit development. I find exploit development is somewhat misunderstood because while vulnerability research is really awesome, O-days and bugs seem to grab headlines and get all the glitz and glamour, but all of the work behind building a production level exploit kind of is overlooked or taken as a given after a bug is found. And in reality, there's significant preparation that's required to get an exploit to production like value, ready to go, one click, and hit. I'm sorry, this is bothering me, so I'm just gonna put it back on full screen. I am really sorry about that, guys. Let's start over. I'm Valentina. It's great to be here with all of you today. Let me tell you a little bit about why I'm doing this talk. I find exploit development is typically misunderstood. VR gets all the glitz and glamour, but I chose this topic not only because I am passionate about exploits, but also because of my role at IBM X-Force gives me a unique perspective on the whole development life cycle of exploits, which is not really common in those that participate in the life cycle of exploits. Like, it's not really usual for the exploit developer or the bug finder to be the one to actually get to deploy the exploit on a real life environment, which is a process that I get to oversee, and I'm fortunate enough to participate in all of those steps. So I am going to share those insights with you today. Oh my gosh. Okay, so what is an exploit? An exploit is a method or a piece of code that leverages vulnerability in software, networks, operating systems, hardware, or anything else to trigger behavior that was not intended by the designer or the developer. Now, one of my biggest pet peeves is using the word find in combination with exploits. Have you ever heard that before, or maybe you're guilty of it? Why is that my pet peeve? I promise you it's not because I'm a pedantic nerd that can't help but correct people. There's really a reason for it, and the reason is because the distinction is important. Vulnerabilities are found and exploits are built. And so the reason why I don't like the term is because using the word find kind of discounts all of the hard work that goes into building the exploit after a vulnerability is found. And one of the points that often gets overlooked is that exploits are software like anything else. And so a lot of the steps to building an exploit have analogous steps, have an analogous step to like building software, mature commercial software in the software development lifecycle, which is kind of why I picked the title. Okay, so what does the timeline for building an exploit actually look like? How long does it take? And the answer varies on a lot of factors, but in the most complex scenarios, it can take months and months of work to actually complete the whole thing. And each of these stages could easily fill a talk in itself. But what I'll talk about with you all today is going to be more of an overview. My goal is to like provide some like high-level context to each of these steps and provide some insights on what kind of goes on each of them. Okay, so not all exploits are equal. So if you've ever tried to run something that you got off of GitHub or exploitdb and it failed, you kind of realize this, right? There's a difference between having a POC that might trigger, demonstrably trigger a bug and maybe cause a crash, or maybe a POC that does demonstrate arbitrary code execution, but it only works on specific versions, or maybe not that stable and only works some of the time, to a fully fledged capability that takes one click and done. And so there's different stages and different forms of quality for exploits. So the first step in the exploitation timeline is evaluating exploitability of a vulnerability. So deciding how realistic is it that you can get arbitrary code execution from a bug or a group of bugs that you may have. And here's where the concept of good and bad bugs come in. Software vulnerabilities will produce an exploit primitive, and an exploit primitive is a generic building block for an exploit. Vulnerabilities should be evaluated in terms of exploitation by the exploit primitive that they provide. So a bad bug is one that doesn't give a very strong primitive or any primitive at all. It doesn't trigger any type of behavior that could lead to arbitrary code execution or can't be built on top of that. And vulnerabilities, of course, are non-uniform. There's many different types of vulnerabilities and vulnerability classes. And there are very many variables to determine how they're useful. And those variables depend on the type of vulnerability. But ultimately, in general, it really does boil down to what can I influence, where, and how. For example, a bit flip at a static offset is going to be less useful than a controlled write at a controlled offset. And so now for weaker primitives, they can be turned into stronger ones via more state transitions, which we'll talk about in a second. And you might also want to consider the repeatability of a vulnerability. So can this primitive be safely triggered more than once? And that makes for a more flexible primitive. And of course, you need to think about exploit mitigations. Mitigations don't necessarily prevent bugs themselves from happening. They're really intended to neuter primitives, exploit primitives. Think like pack that somewhat protects against overwriting function pointers, or CFI that prevents against wrapping to individual instructions or arbitrary instructions, or making certain areas of memory read-only. So your bug might be really strong, but if it can only target one of these areas that's neutered by exploit primitives, exploit mitigations, then the primitive becomes weaker and maybe sometimes ineffective. And ultimately, at this stage, evaluating exploitability is a cost-risk assessment. So you're betting time against a reward, research time. It's probably one of the most difficult steps in the cycle due to the fact that it's extremely challenging to make definitive claims about exploitability in one way or another, meaning it can be really hard to determine whether a vulnerability that's exploitable in theory can't actually be exploitable in practice. I know that exploit developers that I know are typically very cautious when saying something can or cannot be realistically exploited, because if there's some roadblock or some seemingly insurmountable challenge, we typically think that there's just some clever trick that exists that we can get around it, or we could probably figure it out given enough research time. However, you can't spend an infinite amount of time trying to figure it out. There has to be a limit. And that also comes into play when evaluating exploitability. It's kind of drawing a line in the sand of like, okay, how much time do I want to give myself to work on this, and how much time do I want to risk against the reward of a fully fledged exploit. So now we're getting into the actual exploit construction, the fun part, of which the first stage is primitive construction, building on top of that initial exploit primitive that you got from the vulnerability. So I can't talk about exploits without mentioning weird machines. And a weird machine is essentially a computational artifact where execution occurs outside of the original specifications of the program. And triggering a bug causes a system transition from normal machine to a weird machine. Halvor Flake has an excellent presentation called Limiting Weird Machines. I recommend you all check it out. He builds a very intuitive model on how to think about weird machines, which I'm briefly going to borrow for this talk to talk about exploit primitives construction. A program can be modeled as an intended finite state machine running on an underlying CPU with, say, n bits of memory. And so each bit of the CPU can be either 0 or 1, which means that there's 2 to the n possible, 2 to the n nodes in this state space. And so the execution of a program traces out a path in this state space. For every combination of state and CPU instruction, there's an edge leading to the next state. Here, the colored nodes represent the sane states or the intended states of the program. And of course, there could be different combinations of sane states depending on control flow. So when a bug is triggered, execution gets knocked off the sane state path and enters this weird state. As we can see here, jumping from the colored sane state node to an undefined state node. So now the instruction sequence is applied to a weird state. Each instruction will jump to a new unknown state outside of the sane path. When constructing an exploit, the idea is to be able to create a path from the initial weird state to any other state. From a concrete perspective, we want to think about what types of atomic operations can we perform using the undefined application behavior, and how can we link them together to create a Turing-complete weird machine. And so this process looks different for different vulnerabilities. Say you have an out-of-bounds read vulnerability. You might research how to turn that into an out-of-bounds write vulnerability, which is a more powerful primitive. And from the out-of-bounds write vulnerability primitive, then you might take that out-of-bounds write and turn it into an arbitrary write primitive, and finally turn that arbitrary write, where you can control any contents to any address, into arbitrary code execution. So you don't just have the bug to trigger, to control the state space or the memory state. You can also leverage the normal program behavior to influence the memory state. In this example that I've depicted in this slide, this uses heap grooming to control adjacent memory and turn an out-of-bounds read to an out-of-bounds write. But even after constructing most of the exploit primitives that you need, your job might still not be done after that. Which leads us to this next stage of the exploit construction, which is refactoring or reconstructing your exploit primitive. One of the reasons why you might need to do this are exploit mitigations. Essentially, exploit mitigations serve to reduce the number of reachable states from a weird state. For example, address authentication mitigations like PAC or MTE will bend many edges to the segfaulting state. So you can't do all those state transitions to all the intermediate states in the space. It just takes you right to segfault. So mitigations require a contortion of primitives, additional steps or state transitions to achieve stable code execution, oftentimes requiring additional vulnerabilities such as an information leak to supplement your original primitives too. So getting around those like address authentication mitigations, for example, you'd use an info leak. So now finally, after all of that, we have arbitrary code execution. So we've chained together all of the exploit primitives, all of the bugs in our chain to achieve arbitrary code execution, and now we have a Turing-complete weird machine. And this is where we're riding high. This is the fun part. So just to keep quick recap on what we have so far, we have a bug, identified a crash, we've assessed its exploitability, we've built a primitive chain, rebuilt the primitive chain as needed, we can execute a weird machine, and finally we have arbitrary code execution. Now, most public proofs of concepts kind of stop here, or before this even. But because we want to create a fully fledged, mature exploit that can be used in a real environment, our work is not done. Which takes us to the next part, where we're riding high, we're really proud of ourselves because we did the cool thing. But now we have to think about chain stability, which is really important process in this step. And the reason why is because exploits are not deterministic, meaning the behavior when you run an exploit could change across exploitation attempts. So before I competed at Pwn to Own this year, and if you don't know what Pwn to Own is, it's basically like a live exploit code demonstration. I was trying to explain what it is to friends and family. And after explaining to them that no, people are not going there and finding ODAs and building exploits right on the spot, and trying to explain that if that was possible, we'd be in really big trouble, they were just like, wait. So what's the point? Like, why are you nervous about it? You're just going to go run your thing and that's it? Who cares? You're done. Just test it on your machine. It's fine. And I needed to explain that actually a lot of things can go wrong, and they do go wrong if you ever watch the competition. And again, this is a common theme in my talk. It depends. Reliability does sometimes depend on the nature of vulnerability or exploitation technique. Not all vulnerabilities produce unstable behavior. That's part of the reason why you might hear some discourse around which is better, memory corruption or logic bugs, because logic bugs are kind of considered to be more stable than memory corruption bugs, and the behavior might be easier to predict. Some things that might impact stability are the vulnerability requires getting the system to a specific state to be able to trigger it. It might require winning a race condition, which is not always reliable. Mitigations can also impact stability. A lot of mitigations include a factor of randomness and introduce conditions that thwart individual exploitation attempts. But the goal is to increase exploit reliability to 100% such that one trigger means successful pwning. So now how do we get from POC quality code to where it works most of the time and on most systems maybe, to a mature exploit that works no matter what every single time? You will want to refine your primitives. Some examples of that are tightening race condition windows or widening race condition windows, where you make it so your exploit wins the race condition every single time. That might include adding like triggering a slow path for what you're racing, making your memory sprays more precise and ensuring that the layout of your memory layout is exactly as how you need it to be. You might swap gadgets or objects to more reliable ones, and overall just refining the exploit a little bit to make sure that the reliability is 100%. This might also require developing new primitives, like we said before, like Oracle primitives to bypass some randomness mitigations. And essentially, you need to analyze all of the program's control flows and refactor your exploit code so that it's able to deal with all of the possible scenarios that might happen during execution. I'll also mention cleanup at this stage. This will come into play a little bit later, but it also comes into play for stability. So you want to release all of your used resources, destroy all your objects, free all your memory, close all your handles, and make sure that post-exploitation, the system behaves exactly as it was before. And preferably, if you're exploiting an individual program, that continues executing like nothing happened. The goal is to minimize exploitation side effects and restore everything to its original function. So I've presented the exploitation timeline as linear, but in reality it might look a little bit like this, right? One roadblock might land you back to square one. Or conversely, you might have had some of these steps sorted out from a previous bug, so you don't have to do some of these things that I talked about before. But in general, starting from scratch, you'll have to do all of this. So now we've moved on from the actual exploit construction to real-world deployment considerations, the first of which is versioning. So what versions of the target will be supported by the exploit software? In general, the more specifically target the exploit, the better, and that's because the broader product targeting means that you have to deal with more variants. Different versions of a product have differences that can impact exploitation. Some examples are types of objects that are available and object sizes, implemented program features, offsets, signatures, available gadgets, drastic differences in programming logic, and implemented or supported exploit mitigations. I have a funny story about this. When I was working on my Pwn2Own exploit, I had it working perfectly like 2 months before the competition, and all I needed to do was hope that my bug didn't get patched. And it was working perfectly on Windows 10, really stable and beautiful. And then I went to test it on Windows 11, and it crashed. And so you might think, well, okay, Windows 11 has all those, fancy exploit mitigations. Maybe it was something like that that thwarted the exploit. But no, that's not why. So a few years ago, Microsoft deprecated one of their memory allocation APIs in the kernel. I think it's called EX Pool with tag. And only on Windows 11, they replaced all of the calls to this with the new one in the NTOS NT kernel. So there's only one difference between the deprecated one and the new one. Can anyone guess what it is? No? The only difference is that the memory is zero initialized. So before returning the pointer, all of that memory is zero initialized. The reason this is done is to prevent information leaks. So if that buffer is returned to user space and it's not zero initialized, you might get some information leak from the previous allocation in the kernel, and that's bad. But this also had the secondary side effect of ruining my use after free race condition because it was a really tight race window, and so if that memory was zero initialized, then that caused a null pointer dereference, causing the whole machine to crash. So now I needed to find a whole new object to spray using either the old deprecated API, but I couldn't use anything in the kernel, or using the new API that specifically passed in an uninitialized flag, telling the kernel to not zero initialize that memory, which severely limited the types of objects that I could use. I did eventually find one, but that really limited the flexibility because the original object that I used to spray was elastic in size and content, and the new object that I chose was neither elastic in size and did not have any controllable content that I could control. So that was added weeks of extra work just so I could target Windows 11 for the competition. So just like in the example I mentioned, the story I just told, different versions of the exploit might need to run differently depending on the target. And at this stage, targeting and fingerprinting is about determining how the exploit will know which of those versions to run. If it's a remote exploit, is there a way to do remote fingerprinting? If it's local fingerprinting, will the exploit self-modify once it has the required information? Or what information will be gathered before deploying the exploit so that there's only one version that could possibly run? And there are various ways this can be done, depending on what kind of exploit it is, local or remote. Some ways include like in-memory pattern matching, using an API call to return system version information, reading system files, analyzing like service response metadata, like a banner from a network response, or you can also just gather that information before and only deploy one version of the exploit. And now this is one of my favorite topics to talk about, but environmental considerations. So exploits in the real world have a lot of difficulties. And that's because real-life systems are hard to emulate, like with real-life traffic and real-life users. The more details you have about the target, the better. So you can more closely emulate what's going on there. And you can try to approximate real systems by creating inorganic system noise. One way to do this is using like performance testing tools or like stress testing that's available in various development kits to try to simulate noisy environment. And so some things you might want to consider. System load can affect reliability. So like network traffic and running programs can use resources that interfere with the exploit. So like think about a memory corruption exploit or like a use after free. Some program might request that memory before your exploit has a chance to reallocate the vulnerable object or something like that. And there also the concept of low resource versus high resource environment really can affect exploit execution. For example, exploiting a race condition requires a minimum core count of 2 because you have to have 2 simultaneous threads running to be able to win a race condition. So I have a funny story about this, which is we were deploying an exploit for a client, and the client ran CrowdStrike. So I was testing my exploit against CrowdStrike, and it didn't work. And I was freaking out, thinking like, oh, they detected some malicious behavior or something. But no, what actually happened was the API that I was using to spray, which I called thousands of times to allocate thousands of objects, was hooked, and hooked by CrowdStrike, and each of those calls was slowed down by an order of magnitude. So my exploit just never finished running. It wasn't that it wasn't successful, it just took it would have taken like hundreds of hours to run. So things running on the machine, not necessarily related to security, it can impact how your exploit runs versus just testing on a plain development machine that has nothing going on it. So this takes us to the next stage, which is in the real world deployment considerations, which is stealth. So there's a concept of being burned that you might have heard about. And so this just means that your exploit has been recovered, or it's no longer it's no longer in just your possession. Somebody else has caught it. And so this is only relevant for things that need to stay private, so not anything like that's going to go into public disclosure or to be released publicly. Last year, you guys had Maddie Stone as your keynote. She did some wonderful work in the wild detection exploitation for Google Tag, and as she said, as she told you, in the wild, exploits have been increasing. So we can only infer that detection technology has matured. And being on the offensive side, you kind of need to be able to blindly anticipate how those in the wild exploits are being detected so that you can avoid your exploit from being detected and being on one of those year-end charts that Google releases. So knowing what you're up against is crucial. Having an EDR lab is important, but even that can be kind of tricky because offline labs for EDR are tricky because the EDR might not respond the same way if it's connected, calling back to home, then disconnected offline. And also, specific EDR configurations can impact detection behavior. So you might not necessarily have the information of how a target's EDR is configured, and so depending on that, things can alert or not. And also, the most valuable targets may be monitored by solutions not available to the public. So this is always tricky to determine what you're up against, and so having the most amount of information is the best. And so other steps of the exploit development cycle can come into play here. So stability. Does the exploit crash? Because if it crashes, then a crash dump might be produced, and that kind of gives away your whole bug, right? Cleanup. Does the exploit release all of these resources, or does it leak a bunch of memory to make it really noticeable that something's gone on after exploitation? Does the system continue functioning as normal, or can the user kind of figure out that something wonky is going on? Exploitation primitives, are they known? Are they public? Can they be signatured? So bug triggers are kind of difficult to signature because you can't anticipate when a bug is going to occur. And if you could, then the bug wouldn't exist, right? But exploitation side effects are easier to signature because they have a tangible outcome. So something like credential overwrites, token swapping, function pointer overwrites, changing values in important memory that you can hash the before and after. Those are things that are kind of easy to figure out if they've occurred. So exploit primitives are more likely to be signatured than bug triggers. And of course, environmental considerations. What's running on the target, EDR, or even other adversaries. And some other considerations that seem minor but might have a big impact. So like size, is your exploit artifact, are you transferring like gigs and gigs? Is it a small native binary, or is it like some weird script written in a weird scripting language that executes from like a shady folder or something? Methods and preparation. So within your exploit, are you calling weird APIs that only exploits call, or are you, doing something stealthier, like maybe using direct syscalls or something like that? And last but definitely not least, which might seem funny, but strings. So if there are any malware analysts in the room, they can verify that a lot of exploits do not strip their strings. And that's like a major easy way to reverse engineer an exploit is just by reading its strings. I have a funny story here. Like one of my first projects when I was studying in boot camp was to write a keylogger. And the goal was to write the stealthiest keylogger you can, and then the other team was going to hunt you on the machine. And so I spent a week staying up all night developing a novel keylogging technique that had never been, that was novel at the time. And I was so proud of myself, deployed the whole thing, and I got caught on the first day because I didn't strip the PDB string from my binary. So the bottom line is you want to minimize the unavoidable side effects of exploitation and make it like you were never there. So now this takes us to OPSEC attribution. And this might seem like it's kind of like stealth, but distinctly different. So stealth is about hiding as best as possible. OPSEC is kind of about minimizing the damage control if you're caught already. So design decisions at the stage largely depend on the actor and their goals and can be kind of subjective. So not all there's no best solution for this. And the stakes can be high depending on the actor. So some things to consider are like binary artifacts, like I just talked about, can be inadvertently left behind by compilers or other things. So there's a decision to be made there. Do you strip it? Do you manipulate it to shift attribution? That's the decision you have to make. Applying anti-reverse engineering or obfuscation to your exploit. So if it is recovered, making it really hard to analyze, reproduce, or understand, so maybe your bug might not get patched right away. Or you can conversely try to make it look innocuous like a normal system thing. Techniques and coding styles. So specific primitives and techniques might be associated with specific threat actors. So if you've ever read like a Google tag report about an in-the-wild exploit, they often mention exploit primitives being associated with certain actors. So like certain actors prefer to use like specific exploit primitives or objects or have similar exploitation styles that kind of become known with the group. So if you want to minimize what can be burned if your exploit is caught, maximizing novelty isn't always the best strategy. It's kind of a cost-risk assessment, right? You might want to use things that have already been used publicly for one, to not call attention to the exploit and make it seem like run-of-the-mill, something that's already been seen before, shift attribution, and then minimize your new novel strategy and kind of keep that for a higher stakes operation or something like that. And again, you also want to separate your post-exploitation tooling to minimize that getting burned as well. So only burning as few things as possible. And finally, we've gotten to the testing and maintenance part of the timeline and other exploit DevOps considerations. This is me when the offsets change on the exploit. At the end of the day, exploits are just software, and they need to be tested and maintained, just like real software. So doing things such as proper documentation so operators know how to use it, testing against all targeted versions and environments, unit testing exploit primitives. You might want to set up a automated CI/CD pipeline to run your tests automatically when you push new changes to the exploit, so you don't have to do all of that stuff manually. And of course, fixing up the tool chain when unexpected situations inevitably pop up. So dealing with bug reports for your exploit that triggers a bug. And keeping up with new OS software builds. So that's where the maintenance part comes in. So whenever a new version comes out, testing the exploit and making sure that everything still works as intended, and when it inevitably breaks, fixing it for the new version. So some conclusions. Exploit development is hard, and there's a lot of grunt work that goes outside of the initial rush of getting arbitrary code execution. So it's its own art, separate from vulnerability research, although the two go hand in hand. Many people do both, but it is its own art. And a lot goes into weaponizing a bug. The complexity of this timeline and this life cycle makes it so that actors with more resources and researchers have a big advantage. Sophisticated exploit development is highly skilled work. It's very niche, and very few people are doing it for free. And the bar is high, which is why we don't really see mass exploitation of the critical vulnerabilities found in high-value targets. It seems like every other day we read reports about fear-mongering about the latest critical vulnerability and that you need to patch immediately or risk total ruin by hackers. And you should definitely patch as soon as possible, but due to the time and skill needed to develop a one-click and go exploit that could be used by like script kiddies in the masses for public consumption by your run-of-the-mill internal cybercrime groups, it's really unlikely that that is going to happen overnight. It takes a lot of work and a lot of resources. Of course, there has been some exceptions, but those have been in exceptional circumstances, right? So we did see a few years ago, the Eternal Blue being used in massive ransomware campaigns, but that was an exceptional circumstance where the tooling was leaked from an actor with a lot of resources that had already productized the exploit. It wasn't a community-sourced exploit or anything like that. And that's it. Thank you so much to these people for helping me out, giving me feedback on my presentation. And I don't know if there's any time, but if there is, I'll take questions.